Simplifying radicals can get a little challenging when we have larger indices, but if we understand our power rules or our exponent rules, things get a little simpler. So, let's look at these couple of rules to remember this. If we have a power, a to the m to the n power, we have a rule that says we multiply the exponents. Well, where is that coming from? Think about a squared to the third power. All this means is we have 3 of these a squareds multiplied together. That's what cubing means. So we have 3 of these things multiplied together, and they're all a squareds. And a squared just means a times a. So this is a times a times a times a times a times a, which just means we have 6 a's altogether. We have 3 groups of 2. So it's pretty straightforward to see that we have a to the 6th. So we're going to multiply these. If this was 12 and 3, this would be 12 times 3, which would be 36. Then if we have a product to a power, well, that power just affects both of these. All right, so if we have, for example, if we have ab to the third power, well, this just means we have ab times ab times ab. And this is all multiplication in between here. In between these is all multiplication. This is a times b times a times b times a times b, which if we rewrite that, because we know that multiplication is commutative, which means we can flip these things around as much as we want. This is the same as multiplying all the a's together and then multiplying all the b's together. It doesn't matter what order we multiply if we're just multiplying. And this is just a cubed, b cubed. All right? So the moral of the story is that exponent just gets applied to both of them. All right, so keeping that in mind, we're going to use those, but we're actually going to use them in reverse. So our strategy here is we want to write the radicand, that's the thing underneath the radical, as a power that's equal to the index. Then that gets wiped out, all right? Simplifying the expression by canceling the power and the roots, all right? And then we got to watch out, because when we have positive, or actually this should be even indices that simplify to odd powers, they're going to need some absolute values. So let's try some out. So we have a fourth indice there, or an index of 4. So our goal is going to be to rewrite the stuff underneath that is something to the 4th power. That's our goal. Well, we know we have an a to the 4th power. Let me leave that alone for right now. But this is something to a 4th power. I think it's a 2 to the 4th power. Is that right? Check that out. I think it is. 2 times 2 times 2 times 2 is 2 to the 4th. All right, and if it's even, you might always check 2. So this is really 2 times a to the 4th power. And that's good news, because these guys are going to wipe out a 4th root of a 4th power. They're opposites. They cancel each other, and so we're left with 2a. And since we started with a even indice, we've got to look. What's our powers? It's a 1. So even indices have to come out with positive answers, so we're going to put some absolute values there to make that positive. Or technically, we only need it around the a, because that's got to be positive. It's a principal root. The 5th root, we want this to be all 5th powers. And so x to the 5th is already there. Negative 32, well, that is negative 2 to the 5th power. So, you know, if it's an even one, you might just check that it's a multiple of 2s, or a power of 2 specifically. So this is, we could write this, and this step we might skip here after a little bit, but that's the same. Negative 2x to the fifth, it means negative 2 to the fifth, x to the fifth. So we just use that rule in reverse. And this is going to cancel, leaving us with negative 2x. Now we started with a odd index, so we don't need to worry about absolute values. How about this? This is a square root, so an index of 2. So we want to write these things as powers of 2, something to the second power. All right, well, let's rearrange this a little bit. This is 49 is 7 squared. And this is x squared and y to the 6th. And now we're going to use this rule in reverse. Use both these rules, actually. So we're going to pull a power out, but notice that when we have a power to power, it multiplies. All right, so if I have a to the 6th, I can rewrite that as a squared cubed. Or if I wanted, I could write it as a to the 3rd squared. Well, we're trying to write this as something squared because that square root will cancel that out. Well, if I have a 7 here, this 7 squared equals that. These two things have to be equivalent. Then I have an x squared. All right, so let's put an x there. And then I have a y cubed. Well, actually, let me back up here. That's supposed to be a 4, right? What happened there? So we actually need an x squared here because, remember, power to power we multiply. X squared squared is equal to x to the 4th. And then we have these y's. I've got y to the 6th, so I'm going to need to divide that 6 by 2 and get 3. These two things here are equivalent. So this guy right here is equivalent to this thing here. Double check. Square this, y to the 3rd to the 2nd, multiply those, you get y to the 6th. X squared to the 2nd, that's x to the 4th. 7 to the 2nd is 7 to the 2nd. So that's what we have there. So that index that's squared, the square root with that little invisible index of 2 there, cancels out this squared here. And so we're left with 7x squared y cubed. Okay. Now, even indices, this has an index of 2, even though it's not written, that leads to odd powers. That is going to need an absolute value. All right. You can put an absolute value around the whole thing, or usually we'll just put it around the odd power. Because if y is a negative number, negative 1. Negative 1 to the 3rd is negative. That would make this whole thing negative. But it's a square root. A square root cannot be negative. When you take a square root, it's got to be positive. And one more, cube root. So we've got a cube root. Our goal is to make everything in 3rd powers. So this is 27, which is 3 to the 3rd power. And then a to the 3rd is already a to the 3rd. And then we have b to the 12th. Well, let's see, that's b to the 4th cubed. Because 4 times 3 is 12. Right? So, everything's to the 3rd power there. So this is 3 times a times b to the 4th cubed. Ask yourself, does all of this equal all of this and equal all of this? It does. We just changed the way it looks. 3 to the 3rd is 27. A to the 3rd, right there. B to the 4th to the 3rd, 4 times 3 is 12. And these guys will cancel each other out. The cube root of something cubed, those are opposites. So this is 3ab to the 4th. All right. Now, that's all there is to it there. You might notice that there's kind of an extra step here. Once you get a good handle on it here, this step can be skipped here. So this one is optional. We can just see that this guy we have the fourth powers, so these 4's cancel basically, right? So the fourth power and the fourth root are going to cancel. Same idea here. This step here really is optional because once we have this, these 5's are going to cancel, negative 2 to the x. But you do need to take the time to break it up. You do need to take the time to write it out there, all right? So here we kind of did skip that step. This is a good one to write. Notice that the powers are just getting divided by the index, basically. Okay? So this guy here is an optional. The one up above had a little more going on there, but all right, hope that helps. Hope that gives you an idea of how to simplify a radical with an index bigger than 2. Good luck.